So we'll wrap up day 2 of our executive summary of volumes in calculus with something that's not technically a volume of revolution. It is just a regular volume. So if you have a right square pyramid, so that means you've got a square base. You could do it with a triangular base or any other consistent area base, but for our purposes today, a square base is going to be a little bit easier. You can add up the volume by integrating with the more general term that we had. So that's our volume is the integral from A to B of the cross-sectional area of the shape with respect to that variable. So we are going to do it from the bottom up. Now let's say we've got a height h and that the square on the bottom has a side length s. Then if we were to orient it so that this dashed line connecting the center of the base to the peak of our pyramid is the positive x-axis, then we would be dealing with a shape like this, with square wedges along the way. And this would be the source of our integral. So we'd have this point at 0h, or sorry, that one is h0, this point is 0, 0, and this line peaks at the point 0, s over 2, because this whole thing is the length of one side of the pyramid. So that height is just half the height. So what we need to figure out then is the length of the side of a pyramid, or that slice of the pyramid when you're just an arbitrary x units in. So this will be similar to the cone. We won't be doing that integral of pi y squared we did with the cone because these aren't circular bases. We're going to be doing just the general area. But this area is going to depend on this shape. So the length of that shape, or of this side, is going to be double the side of the length of the line here. So we have, again, a y equals mx plus b form. We know one point is s over 2 and 0, so that means our b, our y-intercept, is s over 2. We also have the point h. So we can use this to determine that our slope is a negative 2h over s. No, sorry. Did the mental math wrong. It's a negative s over 2 and h. I had that reciprocated. So here is our slope. That means our line is y equals negative sx over 2h plus s over 2, or s over 2 times 1 minus x over h, where s over 2 is a constant. Now that is the side, or the distance to that y-axis. To turn that into area, that's going to be 2y squared. So that's s squared 1 minus x over h squared. If we felt like it, we could get rid of these denominators. Turn this into s over h squared times h minus x squared. This would also work, but this is our expression for the area. So the area of our pyramid then, or the volume, is going to be the integral from 0 to h of our area dx. Again, S over H is a constant. And the argument in brackets works out to h squared minus 2xh plus x squared. So we have S over h squared, integral from 0 to h, of, oh, sorry, now it's not the integral. We'll skip to the completed integral from 0 to h. We now have h squared x minus x squared h plus x cubed over 3. Now this whole thing is going to be 0 when x is 0. So then our volume here, when we have x equal to h, gives us h cubed minus h cubed plus h cubed over 3, and then again we're subtracting the 0. These cancel. This h squared we have here cancels with 2 of these h's, and we are left with a volume equal to s squared h over 3. We could go through this and deal with a rectangular base or a triangular base. All we need to do is come up with the expression that represents the area of a cross section as we're moving through the shape. So as we lose symmetry, the equations become more complex, but that doesn't mean it's not doable. So we've got now the general toolkit of the principles in place. And when we continue with this on day 3, then we will take a look at doing integrals over volumes that have gaps in the middle.